Okay, last section we talked about exponents and exponential functions. This section we're talking about logarithms and logarithmic functions. Remember those lists of numbers that we played around with last time? I mentioned that, like in this list of numbers, the blue numbers are the powers or exponents that you raise 3 to get the black numbers. 3 to the 1 power is 3, 3 to the 2 power is 9, 3 to the 3 power is 27, and so on. So another way of saying that is that the blue numbers are the base 3 logarithms of the black numbers. The base 3 logarithm of 3 is 1. The base 3 logarithm of 9 is 2. The base 3 logarithm of 3 is 20, or of 27 is 3, and so on. In this list, where the black numbers are all powers of 2, the blue numbers are the base 2 logarithms of the black numbers. They are the powers that you have to raise 2 to get the black numbers. So in general, logarithms are exponents or powers that you have to raise one particular number to get another number. So if I'm saying, what power do I have to raise 2 to end up with 32,768? Another way to ask that question is, what is the base 2 logarithm of 32,768? And the answer is 15. So when you ask your question like, what power do I have to raise one number to get another number? You could say that same question using the words, what is the base A logarithm of B? So relating to some of the examples we were looking at last time, you could ask questions like, on which square of the chessboard are there 1 million grains of rice? What does x have to be so that 2 to the x power is 1 million? How many years before the population of Happy City reaches 200,000? What does x have to be before 100,000 times 1.03 to the x power equals 200,000? Or just 1.03 to the x equals 2? Or just, what does x have to be for 4 to the x to equal 5,000? Those are all the kinds of questions that we use logarithms to answer. So to say log to the base A of x equals y means the same thing as saying a to the y power equals x. So those are two different ways of expressing that relationship among those three numbers. You can express it in logarithmic form or in exponential form, and you can translate back and forth. So if we start with log to the base 5 of 1/25 equals -2, how would you write that in exponential form? What to the what power equals what? Answer, 5 to the -2 power equals 1/25. Let's try another one. Log to the base 3 of 81 is 4. In exponential form would be what to the what power equals what. So notice the base on the logarithm is the base of the exponential expression. It's the number that's being raised to a power. What the log is equal to is that power. It is the exponent. And then what you're taking the log of is what that exponential expression is equal to. So here that would be 3 to the 4 power equals 81. Now let's try some in the other direction, going from exponential to logarithmic form. 3 to the 5th power equals 243. That would be that log to the base what of what equals what? Answer, log to the base 3 of 243 equals 5. Notice the number that you're raising to a power, the base of the exponential expression, is the little subscript number by the logarithm. It's the base of the logarithm. The power is what the logarithm is equal to, and then what 3 to the 5th power is what we're taking the logarithm of. Let's try another one. How would you write 7 to the 3 power equals 343 in logarithmic form? Log to the base what of what equals what? Answer, log to the base 7 of 343 equals 3. So if we think in terms of functions, last time we talked some about exponential functions. So if you pick a particular number like 3 or 4 or something, and you look at the function 3 to the x power or 4 to the x power or something like that, one of the things we said is that that is a one-to-one function, and that means that it has an inverse. And the inverse is a logarithmic function. The inverse of the function 3 to the x would be log base 3 of x. The inverse of the function 2 to the x would be log base 2 of x. The inverse of the function 4 to the x would be log base 4 of x. And here's a graph showing the function that takes x and gives you 4 to the x power, and then the inverse that takes x and gives you the base 4 logarithm of x. So with the red exponential function, you could, for example, plug in 1, and you would get out 4 to the 1 power, which is 4. So when x is 1, y is 4. With its inverse, the logarithmic function, you could plug in 4, and you would get the base 4 logarithm of 4, which would be 1. So when x is 4, y is 1. If you plug 3 into the exponential function, 4 to the 3 power is 64. If you plug 64 into the logarithmic function, the logarithm to the base 4 of 64 is 3. So the logarithmic function undoes what the exponential function does. So you can have a logarithmic function with any base that would work as the base of an exponential function. Pick a different number, you've got a different particular logarithmic function. This is the one where we are talking about base 4 logarithms. But that base on the logarithmic function could be any number greater than 1. And technically, it could also be a number that's less than 1, but still greater than 0. But it's more common for the base to be a number greater than 1. So in that case, the graph of a logarithmic function like that always has sort of the same basic shape. It might be a little steeper or a little flatter, but it has this sort of a shape to it. The domain is the open interval from 0 to infinity. That means it's only the positive numbers. You can only have the logarithm of a positive number because the result of taking 4 or any other number to a power is always going to be a positive number. So log is only defined for positive numbers. The range is all real numbers, negative infinity to infinity. So what you get out of a logarithmic function could be any number, could be negative, could be positive, could be 0. The place where it's 0 is if you plug in 1. So the log of 1 is 0. And that shows up on the graph as the x-intercept, 1, 0. A function like this is always going to be an increasing function, so the bigger x is, the bigger the log of x is. It's a one-to-one function. Its inverse would be the exponential function, a to the x. The y-axis is a vertical asymptote for the graph. So it looks like the graph is touching the y-axis, but if you really zoom in, it never quite touches it. It just gets really, really close to it. The graph is continuous on its whole domain. It doesn't have any holes or gaps or jumps. And because these two functions, the exponential function and the logarithmic function, are inverses of one another, their graphs are reflections across the diagonal line where y equals x. Some more properties that are true of any base logarithm. The log to any base of 1 is always going to be 0 because any number to the 0 power is 1. The log to any base of that same number is always going to be 1 because any number to the 1 power is that number. If you start by taking a to the x and then you take the base a logarithm of that, you're back with the number you started with. So the log undoes what the exponential function does, and vice versa. The exponential function would undo what the logarithmic function does. And because logarithmic functions are one-to-one, if log base a of one thing equals log base a of another thing, then those two things must be equal. I said that the base of a logarithm could be any number greater than 1, or less than 1, but still greater than 0. But there are two numbers that are used most commonly as the base of a logarithmic function. One of those numbers is 10. And because the log to the base 10 of a number is used so commonly, it's called the common logarithm, and it's often written just without the little 10, just as log, L-O-G, of x. So if you have a button on your calculator labeled LOG, that's what that button does. It gives you the base 10 logarithm of whatever number you ask for. So log without a little subscript usually means the base 10 logarithm. I say usually because sometimes in higher math, it's used to mean a natural logarithm, but probably for natural logarithms, you'll only ever see it written as ln. So that's the other special logarithmic function. When you use the number e, remember we talked about that last time, e is that number 2.71828 and so on. If you use that particular number for your logarithm, that's what's called the natural logarithm, and it's abbreviated ln. L for logarithm, N for natural. So ln of x means the base e logarithm of x. And your calculator probably has a button on it labeled ln that will give you that, the base e logarithm of a number. So ln of x, or log to the base e of x, is just one particular logarithmic function. It's the one where the base is e. And so the ln of 1 is 0 because e to the 0 is 1. The ln of the number e itself is 1 because e to the 1 power is e. The natural logarithm function undoes the e to the x exponential function. So if you start with any number for x, take e to the x, and then take the ln of that, you're back where you started. Or if you start with any positive number for x, take the ln of that, and then take e to that, you're back where you started. And just like any other logarithmic function, the natural logarithmic function is one-to-one. If ln of x equals ln of y, then x equals y. Okay, I'm going to stop this video here, and then I'll be back in part 2 and we'll work through some examples.